part 3 really helps us to see that spherical aberrations exist, and it's kind of a fun part, I think. It's going to be just like part 1, so it's pretty simple as far as how we do this. We're going to put a lens. You're going to use the large lens for this one. It's just easier to see the spherical aberrations because it's a bigger surface. Use the large lens, and you have your screen. You'll measure P, you'll measure Q, and you'll calculate F. But we're going to add a little twist to this. I'm going to go to the next page. When you're doing this, you're going to use an aperture to block all but a small part of the lens. So in the first part, you're going to block all of the light except for the light that goes through the center. And then you will measure P, measure Q, and calculate F. We'll call this F1, I guess. I'll call it F center, actually. That's how we do it in your lab manual. So then we'll take that aperture and we're going to move it so that the light is not going through the center of the lens, but instead the light is going through the edge of the lens. Your lab instructor will have an aperture, and you can move that aperture up or down. It only allows light to go through a small portion of the lens. Then you find your P and you find your Q for the new image, and you calculate the focal length of this, which we're going to call F edge. And then to find the spherical aberration is going to be the difference in those two focal lengths. You should find a difference in the focal length by, I don't know, a couple of centimeters or so. That the spherical aberration on a lens like this is significant. That you get a significantly different focal length depending upon where the light is coming into the lens. So, yeah, that's it for that one. It's simple, but it's kind of cool.